In the previous lecture we proceeded somewhat towards deriving the final form of the thin film equations. To do that, what we will do now, or to complete that, what we will do now, we will just write whatever we have derived so far, so that we can go ahead further with that. So, I will just use a part of the board to write remember these are all expressed in dimensionless variable terms. Dash means dimensional body forces per unit volume, right. Then we have the boundary conditions. So, tangential force balance at the interface, normal force balance again at the interface, along with that you have no slip at the wall at y equal to 0, that means u equal to 0. Okay. So, these equations eventually can be manipulated to obtain a velocity profile. So, what we have done, I am recollecting or recapitulating before I will write the final expressions. We first integrated the y momentum equation to get pressure as a function of y, Then we substituted the normal force balance. So, at y equal to 0 at y equal to h, P is equal to Ps, and that Ps we substituted here. So, we obtained a pressure profile. So, the pressure profile is obtained by combining the y momentum equation with the normal force balance. Then once the pressure profile is obtained, that pressure is differentiated with respect to x and substituted here. So, this gives us second order partial differential equation in y in u, and this is integrated twice with no slip boundary condition and tangential force balance boundary condition to get the velocity profile, and that expression I am now going to write. This all we derived in the previous lecture, just for the sake of continuity I am reproducing here. So, u the final form we have got is where we have two parameters A and C2. So, A is equal to where this is A and C2 is okay. So, these are functions of what? H is a function of x and time, therefore, both A and C2 are functions of x and time. Okay. Now, let us see where we are. So, that is why I have written the governing equations and the velocity profile, because we will see what are the equations which we have utilized and what we have not utilized. So, we have in the process, when we have derived this, we have actually integrated this equation twice. So, what we have not yet used are the continuity equation, which I am showing by double tick, and the kinematic boundary condition. Kinematic boundary condition at the wall boils down to the no penetration boundary condition. So, let us use the continuity equation. What we will do is, we will integrate this continuity equation over the thickness of the film. Now what we will do is, we will try to take this derivative outside the integral sign. Question is, can we do it or not? See, this integration is having a limit h which itself is a function of x, right. So, this h is not an ordinary constant, this is a parameter which itself is dependent on this independent variable. Therefore, you cannot just willingly bring this out and in, and you have to use the rule of differentiation under integral sign or the Leibniz rule. So, let us specify the Leibniz rule. So, the Leibniz rule says okay. Hmm? Sorry, yes. Here it is x, of course. In our case, we have variables x and t. So, here it is a function of x only, here it is a function of both x and time. So, only difference is, instead of ordinary derivatives, these will appear to be partial derivatives. So, you write d dx of f here is u. So, u at h, u f at x comma b means u at h, right. So, u at h means u at the interface into dB dx, dB dx here it will be replaced by del h del x, because h is a function of both x and time. U f x a, what is that? U at the y equal to 0. So, u at y equal to 0 is 0, and more or less this, because this is a constant, dA dx is 0. So, this second correction term is 0. So, we are left with somehow I will use only this part of the board because the other part we will keep it. So, this will be now think about it, should we write this as d dx or del del x? See, if this is a function of x only, then this is d dx, but this is a function of both x and t. So, this should actually be replaced by meaning the same in spirit, but conceptually different. I am again repeating, when we wrote a to b fx dy fxy dy, then this b was a function of x only in that example. In this example b is h, which is a function of x and t. So, this derivative cannot fundamentally be ordinary derivative because you already have a function within this which is the function of x and t. So, this will be this is the first term of the continuity equation integrated. What is the second term? So, this is V at h minus V at 0, and V at 0 is 0, no penetration boundary condition. So, these are both kinematic boundary conditions. So, the kinematic boundary condition is used for the y momentum equation. So, you are left with which one is minus? It's okay. So, you are left with now this kinematic boundary condition which says Vi is equal to del h del t plus u del h del x, right. So, u del h del x minus Vi is minus del h del t. This is from kinematic boundary condition, kinematic boundary condition. This is minus del h del t, right. From this equation. So, del h del t So, now we have only one step before to complete before we get a governing equation for H. And what is that step? Integration of u with respect to y. So, integral of y square by 2 over h will be y cube by 6, right. This will be h square by 2. So, the governing equation boils down to where again a and C2 are themselves functions of x and t. So, this equation if integrated will give you h as a function of x and t, which is the solution of the thin film equation. So, this appears to be a bit involved because this is the most general equation that we have written, considering all boundary conditions, all body forces and all possible physical effects combined together. But in some cases certain boundary conditions may become redundant. For example, the curvature effect is not important. So, in that case the normal force balance becomes redundant. So, this equation can be simplified to a large extent in case we are solving specific problems where certain effects are negligible. So, in the next lecture we will try to address one such problem where we will consider the gravitational spreading of a drop. So, you put a drop on a surface and then allow gravity to take its role or to play its role so that the drop is spread. So, we will find out what is the dependence of the height of the droplet as a function of position and time using the thin film model. That we will take up in the next lecture. Thank you very much.